2.6 is about continuity, or points of continuity on a graph. And one way to think about continuity is if you can draw a graph without lifting the pencil from the paper, then it's continuous there. So there's no breaks in the graph, and you can draw it without lifting up your pencil. That's a way to look at a graph and have an idea of where it's continuous or not. And that's actually codified in a checklist. There are three things that happen when a graph is continuous at a point A. The first thing is the y value has to be there. If you look at an idea of a continuous graph at A, here's a graph that's continuous at the point A. I can draw the graph there and not lift up my pencil. Well, what's happening are three things. The first thing is there's a y value there, the circle that I filled in. There's no holes. And so the first condition for continuity is there has to be a y value at A. The second condition for continuity is the limit has to exist. That means from both sides, it has to look like I'm going to end up at the same place when I walk to x equals A. The third thing that has to happen is the limit and the y value have to be the same thing. Otherwise, there'll be a big gap in the graph. So you can tell what's happening with the graph by making sure these three things occur, and it's usually the easiest to do them in this order. A y value exists, the limit exists, the limit and the y value are the same. So let's look at a graph and determine the continuity. So what it says is determine the points at which f is discontinuous. That means find the places where the function isn't continuous. And if it's not continuous there, pick one of those three conditions that describes why. So as I look at this graph, I notice there's two endpoints. Here at x equals 0 and here at x equals 5. There are y values at those endpoints. So the first condition of continuity, the y value exists, is taken care of at the endpoints. The little problem, though, is you don't know what the limit is from the left-hand side of the first endpoint because there's no graph to see. And on the right-hand side, you don't know the limit from the right because there's no graph to see. So when that happens, when you have endpoints, you just need the one-sided limit to exist because I don't have to lift my pencil up off the paper at 0 or at 5. So the endpoints are usually continuous as long as there's a y value there. Well, as I start at x equals 0, I'll notice I can draw the graph without lifting my pencil off the paper till I get to 1. Because there's a vertical asymptote at x equals 1. I have to pick my pencil up and set it back down on the other side to finish drawing. So I know it's discontinuous at x equals 1. Oops. Well, now I got to figure out why. The first condition says there is a y value. When I look at x equals 1, I say, is there a y value here? There cannot be, because that's a vertical asymptote at x equals 1. So no y value can exist. So the reason it's not continuous the reason it's not continuous is because the y value is undefined. There is no y value at x equals 1. That's really what that means. Now I look for the next place where discontinuities can occur. From x equals 1, I can put my pencil and draw the graph until I get to x equals 2. Because notice there's a jump. When I get to x equals 2, I have to pick my pencil off the paper and fill in the circle here to continue drawing the graph. So there's a discontinuity at x equals 2. Well, what would the discontinuity be? The first question, or the first condition is, the y value has to exist for it to be continuous there. But the y value does exist. At x equals 2, the y value is 2, because that's where it's shaded in. So that's not the problem. Now the next thing that has to happen. To be continuous there, the limit would have to exist. So let's look at the limit at x equals 2. If I were to stand to the left of 2, and look down at the graph to see where I'd end up, it would look like the y value I end up with at is 1. So the limit from the left at x equals 2 is y equals 1. That's the limit as x approaches 2 from the left. If I want to find the limit from the right, I stand a little bit to the right of 2 and look where I think I'll end up. The limit as I approach 2 from the right of f of x appears to be the number 2. Because when I'm standing to the right of 2, the y value it looks like I'll end up at is y equals 2. So what that means is the limit as x approaches 2 does not exist because it's different from the two sides. One from the left, 2 from the right. So the reason it's not continuous there is because the limit as x approaches 2 of f of x does not exist. So now we stand again on x equals 2, and we start to walk along the graph. So I walk from 2 until I get to 3. At x equals 3, I have to lift my pencil off the paper because there's a hole and put it back down. So there's also a discontinuity at x equals 3. And we say, okay, well, what's the discontinuity? The first condition is the y value has to exist at a. There is no y value here. Notice since there's a hole and no place is shaded in, there's no y value that goes with x equals 3. So the reason it's not continuous is the y value doesn't exist there. They say the y value is undefined. All the rest of the points of the graph are continuous because I can draw them without lifting my pencil off the paper. Notice after 3, I can draw that whole graph without lifting a pencil off the paper. The other kind of discontinuity you can have is where the limit doesn't equal the y value, and that's usually where there's a big jump in the graph. Let me show you a picture of what that would look like if the limit doesn't equal the y value. Here's an example of a graph where the limit as x approaches a of f of x, if I were to stand on the left-hand side and look at a, it would look like I would end up at 2. And if I stood on the right-hand side of a and looked at a, it would also look like I'd end up at 2. So the limit itself here is the number 2. But the actual y value at a is the number 5, because that's where the graph is shaded in. So this is discontinuous at x equals a, and the reason is because the y value and the limit aren't the same thing. The limit of f of x as x approaches a is 2, and that doesn't equal 5, which is the y value. Or the limit as x approaches a of f of x doesn't equal f of a. Notice it passes the first two conditions. There's a y value, it's 5. There's a limit, it's 2. So it didn't have any problems with the first two conditions. It's the third condition that failed here. The limit and the y value weren't the same. So there's a hole and the point is shaded elsewhere. But this is an example of a graph where the limit and the y value aren't equal, and that's how it fails the continuity condition. So you can tell a lot from a graph, but you should also be able to tell from the function itself if it's continuous somewhere or not. And so generally when we have a function, we're looking for three things. First we see if the y value exists, then we see if the limit exists, and then we make sure they're equal. So in this first example, it's f of x is the square root of x minus 2, and I'm going to use a equal 1. So a is what I'm plugging in for x. And so first I'm going to see if the y value exists, because that's the first condition. So I take every x in there, and I replace it with the number 1 to see if the y value exists, because that's the first condition of continuity. The y value has to exist. Replace all the x's with the number 1, and this turns out to be the square root of negative 1, which is I. I don't know where I would graph an I on my page. So that y value wouldn't exist in a graph with the xy plane. So it's not continuous here. Not continuous at a equals 1, since f of 1, that's my a value, doesn't exist or is undefined. And so that's one way to show a graph is not continuous at a point. You just show the y value doesn't exist. Here's another example. It's a piecewise defined function. And in this case, we want to plug in 1 for x. And when we plug in 1 for x, we can see if a y value exists. Well, what this function says is, if x is equal to 1, the y value is 3. So we know the y value has to exist. The y value is the number 3 by definition. So the next thing we can check is the limit. Does the limit exist? Well, if I look at this function and I examine the limit, I know what happens at x equals 1. At x equals 1, the y value is 3. But to find the limit as x approaches 1, I have to look from the left and the right-hand side. So let's look at what the limit is as x approaches 1 of the stuff where x isn't equal to 1. I want to be a little bit to the left and a little bit to the right to find the limit. So I look at the limit as x approaches 1 of this part of the piecewise function, because this is the part that describes it when x isn't equal to 1. It's a little bit to the left and a little bit to the right. And I can calculate this limit. I can factor the top into x minus 1 times x plus 1. And it lets me cancel the x minus 1's in the bottom. So this limit does exist. It's 1 plus 1, which is 2. So the limit exists, and the y value at 1, that's 3. The limit exists, the y value exists, but it's not continuous because the limit and the y value aren't the same thing. So it's not continuous since the limit as x approaches 1 of f of x doesn't equal the y value there. So that's where the third condition fails. We found a y value, we found a limit. They just weren't the same thing. These next two problems have to do with continuity intervals, and these have to do with understanding domains of functions. The first one is f of x is the square root of 2x squared minus 16. And the thing about square roots is, if negatives show up under square roots, imaginary numbers or complex numbers come out, because i's appear from the negative under the square root. So this thing is only defined. You can only see a picture for this. The domain of this is where 2x squared minus 16 is greater than or equal to 0. It can't be negative, because if it was negative, I'd have negative stuff under the square root, and I wouldn't be able to graph it. Well, where does this happen? Well, I can use the critical value method, or I can graph it in my calculator, but I know that 2x squared minus 16 equals 0. That means 2x squared equals 16, x squared equals 8. X equals plus or minus the square root of 8 is where 2x squared minus 16 equals 0. And so I can take some test points around here to figure out where 2x squared minus 16 is positive or negative. So I guess I could do negative 3 and 0 and 3, because 3 is the square root of 9, which is a little bigger. So when I plug negative 3 inside 2x squared minus 16, I get 18 minus 16, and I get positive numbers when I plug negative 3 in here for x. 9 times 2 is 18, minus 16 is positive. When I plug 0 in here for x, I get 0 minus 16. That's a negative number. When I plug 3 in here for x, again, I get 18 minus 16, which is a positive number. So 2x squared minus 16 is greater than or equal to 0, where I've shaded in the number line here. That's where I get positive answers out when I plug in those x values. So that's the only place it can be continuous. The places where it's greater than 0. So it's continuous on its domain, because that's the only place you get a picture. And to find the domain, you figure out where you get numbers greater than 0 or equal to 0 for the stuff underneath the square root. So this would be negative infinity to negative root 8 union square root of 8 to infinity. And so there's the interval of continuity. It's really just the domain of the function. The next one is nice because it's the cube root. And cube root is an odd root. And since odd powers respect negative signs, by that I mean negative 2 cubed is negative 8. Positive 2 cubed is positive 8. There's a difference. I can take the cube root of negative 8. What number do I cube to get negative 8? That's negative 2. I can have positive or negative numbers under an odd root, so there's no problem at all with this. The domain of this thing is where it's continuous, so this is also continuous on domain. But the domain is all real numbers, because I can take negative numbers under an odd indexed root, because odd roots respect negative signs. So that function is continuous everywhere because it was an odd root, and odd roots can have negative numbers under them. So the last topic in 2.6 has to do with the intermediate value theorem. The intermediate value theorem is a theorem that is pretty straightforward conceptually, although it can be a little convoluted sounding, by the way they word questions. But the intermediate value theorem pretty much says that if you have a continuous function, that means you left your pencil on the paper when you drew it, then for any y value between the endpoints, there's a point between A and B that has that y value. So here it is in all of its glory. The intermediate value theorem, that's intermediate y value theorem. If f is continuous on some x interval from A to B, well, that just means that when I draw my graph, I don't lift my pencil off my paper. There's an example of one. And L is a number between f of A and f of B. F of A is the y value at A. F of B is the y value at B. And L is some number between them. What the intermediate value theorem says is, I can find some place on the x-axis between A and B. They call that C. So that the y value that goes with that point is the L we saw before. And that has to do with the continuity of the graph. If I'm not lifting my pencil off the paper, then a y value between those two has to match up with an x value somewhere, because I didn't lift my pencil off the paper. So conceptually, it's saying that if you have A and B like this, you can find a number on the x-axis to hit any y value between them, because it's continuous and you didn't lift your pencil off the paper. And this is how they use it in practice. The example is use the intermediate value theorem to show that x cubed minus 5x squared plus 2x equals negative 1 has a solution on the interval negative 1 to 5. And so what I can do is I can show that from this graph. If I can show that, see x value negative 1, x value 5. I'd like to show that this graph is smaller than negative 1 somewhere and larger than negative 1 somewhere else. So that means the y value had to cross negative 1 somewhere between it. We think about this solution as the y value, because y equals that function. So if I look at this function and think about it as y equals, what the intermediate value theorem says is that if between negative 1 and 5 I can find a y value lower than negative 1 at one of these places, and a y value bigger than negative 1 at another one of these places, since the function is continuous, it has to cross negative 1 somewhere. And that place will be where the solution is. So what I have to do to show this is I have to evaluate the function at 1 and 5. And the function I'm using is the thing I want to be equal to negative 1. X cubed minus 5x squared plus 2x. When I plug in x equals negative 1 into this function, I get negative 1 cubed minus 5 times negative 1 squared plus 2 times negative 1. That's negative 1 minus 5 is negative 6 minus 2 is negative 8. So it tells me the y value when I plug in negative 1 for x is negative 8. Now I'm going to plug in 5 for x. When I plug in 5 for x, I get 5 cubed minus 5 times 5 squared plus 2 times 5. That's 125 minus 125 plus 10. So the y value when I plug in 5 here is the number 10. So that means a is like the number 1 and b is like the number 5 in the way that this is set up. And f of a is the number negative 8 and f of b is the number 10. That's the y value at a and b. F of a is f of 1 and f of b is f of 5. So by the intermediate value theorem, since I want this function to be equal to negative 1, I know that it's going to be equal to negative 1 somewhere between these 2 points, because negative 1 lies between f of a and f of b. F of a is negative 1 and f of b is 5. Then there is a number c between the negative 1 and the 5, such that when I evaluate the function at this point c, I'm going to get negative 1 out. So this whole thing is describing how the intermediate value theorem is used. I'm saying that since my value I'm looking to equal is negative 1, and that's between the endpoints, then the intermediate value theorem says that there has to be an x value that has that y value. And that x value would be the solution to the equation.